to the half. And what would that look like? So here's a way of doing it. It's exactly what we did with y equals 2x, y equals x squared. We just draw a little table. So here are some values of x. And remember that we're assuming that those x's are all positive or 0. So we're not going to think about negative numbers, partly because if we try to put in the negative number and ask for its square root, you're not going to get anything out. So square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, of 9 is 3, of 16 is 4. Okay, so the input is 0, gives you output is 0, input is 4, output is 2, input is 16, output is 4. And if you join them up, you get, well, you actually get half a parabola, but it's on its side, is what it really is. So so if you draw y equals square root of x, or better, x to the half, okay, these are the positive values, these are negative values. Don't forget we're not going negative values of x. That's y. Okay, that thing, if you turn it on its side, is basically half a parabola. In fact, it's the corresponding bit to one of these, corresponding bit to that. Okay, because what you're really saying is that x equals y squared, and if you write it out this way, you're saying x is a function of y. If you do that, you've got kind of that picture. That's another way of thinking about it. But for the time being, x is going in and y is coming out. So the square root is, in a sense, a parabola on its side. Okay. Oh, that's what it is. It's the half of the sideways opening parabola. So if we draw x squared, x next to the half on the same set of axes, we get something quite interesting. So in blue, we've got x squared. The black one is just y equals x, and the red one is x to the half. And you notice that when the input x equals 0, then x squared is 0, x is 0, and x to the half is 0. So that's what's happening just there. On the other hand, when x equals 1 as an input, then the output for all three is 1 squared is 1, 1 equals 1, and 1 to the half is also equal to 1. So the same input for all three gives you the same output for all three. In other words, these three graphs, the red x equal to the half, x to the half, the black x, and the blue x squared, all intersect at 1, 1. So all three graphs intersect at 0, 0, and 1, 1. Now, the really important thing here is that when you go from 1 onwards, okay, the x squared, the blue graph, is always bigger than the black one, the y equals x. And that's because that's really x to the power of 1. To the power of 1. And 2, the power of 2 is bigger than the power of 1. So that's why this blue one is always above the black. And 1 is bigger than half. And you notice that the black one, the y equals x, is always bigger than the x to the half, provided you're on the right-hand side of x, that your x's are bigger than 1. On the other hand, if your going to the left of 1, then things switch around, that the x to the half is above the x to the 1. That's because a half is less than 1. The x to the 1 is above the x squared. That's because 1 is less than 2. But that's only for this region between 0 and 1. Most of the time, we're actually going to be interested in the region where x is bigger than 1. So we're actually interested in this relationship that x squared is bigger than x is bigger than x to the half, you know, for all these going on. What we've just done is actually compare these 3 power functions. So we're comparing x squared with x and x to the half. And we're saying that x squared is bigger than x, and x is bigger than x to the half, provided x is bigger than 1. So, you know, for all these values of x. So we've really done a comparison, which is what's happening in this next slide. And there's a general rule, so there's nothing really special about 2 and 1.5. The real thing is that 2 is bigger than 1 and 1 is bigger than a half. And so the general principle is that if you've got one power or one index bigger than another index, so if m is bigger than n, then x to the m is bigger than x to the n. So back here, m this is m is equal to 2, and here n is equal to 1. We've got 2 is bigger than 1, so x squared is bigger than x to the 1. On the other hand, you know, if we compare these two, we could say that here, for our purposes, m is equal to 1, but on this one, the power is so if we compare this, the m is a 1 and the n is a half. 1 is bigger than half, so this one's going to be bigger than that one all the way through. What we say is that the one that has the bigger power grows faster. If you can go back here, what you can see is that another color. Okay. So we pick a value of x here, and we go up here. Look at this distance between x to the half and x. Go out here, the difference will be bigger. Or if we look at the value of x here and look at x and x squared, there's a certain difference. But if you go out here, there's x. How far up do we have to go to get to the x squared? We have to go a long way up. So the difference is much, much bigger further out than it is closer to 1. The difference between x to the half and x is much bigger further out than it is closer to 1. That's what's going on here. We say that the one with the bigger power grows faster than the one with the smaller power. So as you go from left to right, the gap gets wider and wider. So x squared grows faster than x, and x to the 1 grows faster than x to the half. And x to the half, it gets bigger and bigger, but pretty slowly. Y equals x gets big relatively quickly, but x squared gets bigger much, much more rapidly. I just realized you can't see my cursor, can you? No, okay. So x to the 4 grows bigger, grows faster than x squared. X to the 1/2 grows faster than x to the 1. Why? Because the index of 1/2 is bigger than the index of, or the power of 1. The square root of x is bigger than the cube root of x. That just means that x to the half, x to the half grows faster than x to the 1/3. So if we actually do this, let's see. So here's x to the half. Here's x to the half. There's 1. There's 1. So 1 goes in. Square root of 1 is 1. If we drew y equals x to the 1/3, the cube roots, what would happen is that between 0 and 1, it's a bit bigger, but then it tails out and it sort of does this. So it gets bigger and bigger and bigger, but quite slowly, whereas x to the half gets bigger and bigger, but a little bit more quickly, but not as quickly as y equals x. So what's happening? The 1/3 is less than the half, so it grows less rapidly, or the x to the half grows faster than the x to the third. So we're going to apply this. It's called the lines of code model. This is something that programmers and programming managers used to use as a way of working how much time it takes to develop a program, let's say an information system. And the estimated effort, this EM, is some constant times some size of the task to a power. So the estimated effort, this EM, is the person months. So basically, if you say something will take 6 person months, then there's a couple of ways of doing things. Let's see, stop share. So if you say something takes 6 person months to do, there's a few things. You could take 6 people for 1 month, or it could be 3 people for 2 months, or 1 person for 6 months. So the idea is 6 times 1, 6 times 1 is 6. 3 times 2 is 6. 1 times 6 is 6. You could have 2 people working for 3 months, and that would still give you 6 person months. So this idea of person months is just a simple way of how much human work is there involved in developing an application or a program. If you've only got 1 person, it'll take 1 person 6 months. If you can put a team of 6 people onto it, then it'll only take 6 people, it'll only take 1 month. If you've only got 1 person, it'll take 6 months. Then, so that's the effort months. So KDSI is delivered source instructions. So the DSI is basically lines of code, and K is thousands of, so like kilobytes. This is kilo of lines of codes. So if you say 5 KDSI, it means 5,000 lines of code. If you want 15,000 lines of code, it's 15 KDSI. And usually people who are project managers have a pretty good idea of how long it takes to program up a project. The C, the multiplier and the exponent are constants, they're fixed numbers. And we basically have this function, this relationship that y represents the estimated months or the effort months. A is A is the constant, so the constant here is this A here. And X is the input. It's how many thousand lines of codes measured in number of thousands, and that'll be that. And then the N will be fixed according to how complicated the task is. So here's an example. With 2.4 and N equals 1.5, the effort to develop the information system, if you got 5,000, 10,000 or 20,000. So effort months is 2.4 times KDSI to the power of 1.05. Okay. I haven't told you how we calculate to the power of 1.05, but just imagine it can be done. So for 5,000 lines of codes, KDSI is 5 because we're measuring how many thousands, that many, 5. The calculator helps us. 5 to the power of 1.5 is something. You multiply by 2.4 and you get 13. So it takes 13 months. So if you had 13 people, it will take them 1 month. If you had one person, it will take them 13 months. If you had 2 people, it would take you 6.5 months. On the other hand, let's suppose we do 10,000. Okay, if you got 10,000 lines of code, then the KDSI would be 10, and it'd take you 26.9 months. Or if you had, where are we, 20,000, it'd take you 55 months with one person, or if you had 55 people, it'd take 1 month. So you can see that the greater the number of 5,000 to 10,000 to 20,000, okay, 5 to 10 is doubling. And we went from 13 to a bit more than double. So 2 lots of 13 is 26, but we've got 26.93 person months. So doubling the amount of code requires a little bit more than doubling the amount of time required to do it. And if we go from 10 to 20, again, that's a doubling. From 26.93 to 55.76 is 54.8, which is a bit less than what's actually required. So this 55.76 is a bit more than double the 26.93. In fact, this is what's called an exponential growth. That number there is bigger than 1, and we end up with the exponential growth that we've been seeing with this virus of late. So this is really what this line is saying. The fact that the 1.05 is bigger than 1 means doubling the amount of code means that we're going to have more than double the amount of time required, or the amount of effort required. And that's because we've got a power function where this exponential is greater than 1. So the graph increases faster than a straight line, which what's happening here. So there's 2.4, so KDSI on the x-axis, effort months on the y-axis. This is going up, it's curved upwards, it gets bigger and bigger, and eventually it'll get very rapidly big. And if we put in So because the 1.05, because this 1.05, something's happened there. Because this 1.05 is only a bit bigger than 1, this curve is only a bit more curved than a straight line. I'm not going to even try and draw a straight line there. So it increases only slightly faster than a straight line. So another way of doing this, of using this, is suppose you've got a deadline. Is how much code can you actually write in the deadline? So suppose you've only got 18 person months to work on. How much code could you actually write? And the idea there is the following. Normally, if you've got a certain amount of code, what you do is you go up here and then you read across and it tells you how much time it will go. So you're sort of going in that direction. Okay. You know how much code, you know how much time it'll take. The question on the next page is somewhat different. Is that color? It's if this is the absolute maximum amount of person power we've got, 18 person months, going this way, what's the amount of code that you can actually write? So we're sort of going here from 18 person months, how much code can we write? So that's what's happening in this one. So what we're doing is we're saying, we know what the effort months is, but we don't know how much code we need or we can write. So what we do is we solve for this, and it turns out, so we've got an unknown here multiplied by 2.4, so let's divide by 2.4. So 18 divided by 2.4 is 7.5, and we ask ourselves, what value to the power of 1.05 gives us 7.5? So, this way. So, okay, I'm supposed to read this. So KDS I equals something. No, what is it? Well, the way we can get to this is using these laws of indices. So maybe if we write it this way. Yeah, okay. Write it this way. KDS I to the 1.05 equals 7.5. Okay. We're asking what's KDS I, and the trick is if you take KDS I to the 1.05 equals 7.5, and you raise all of this to the 1 over 1.05 and raise that to the 1 over 1.05, that'll give us our answer. What's happening here is that on this bit, we now have KDS I to the, now this is to the power to another power. And we've chosen this, so the 1.05 times 1 over 1.05 gives us 1. So it's quite a neat application of our rules, our power rules. So we've got A to the m, all to the n is a to the m n. So if we choose n to be 1 over m, m times 1 over m just gives us 1. So if we choose this right, that times that gives us 1. So this has to be 1 to the 1.05. Well, that tells us the KDSI is 7.5 to the something. Okay, so that's what's happening. That's what's happening at that line. And 1 over 1.05 actually turns out to be 0.952, and just using your calculator. And your calculator, if you know how to use it, tells you this is 6.8. So basically 6,800 lines of code. KDSI is 6.8. So 6,810 lines of code. So 6.8 times 1,000 can be written. So you know what you can actually do using 18 people for 1 month, or 9 people for 2 months, or 3 people for 6 months, or 6 people for 3 months, or 18 people for 1 month. That's the maximum you can do if you're following that particular model. So just in concluding, you can say that if you've got a project deadline of 18 person months, you can write no more than about 6,800 lines of code. Now, we are relying on our calculator to do these calculations. I haven't told you yet quite what this actually means, but just assume that you can do this. It's kind of a bit like what we do with the to the power of a half. Okay, so that's basically it. What I suggest you do is go and have a look at the problem sheet for lecture 14. We're still quite a bit ahead of time, so we're tracking well. That'll mean that you've got probably another week at the end of the semester. You've got a week at the end of the semester that where we'll have finished this subject, and you've got plenty of time to look at your other subjects for revision. And one thing that I know at least one person asked last week was what's happening with exams, and the answer is the university is looking at exams. There will be, something will happen. It almost certainly will not involve face-to-face exams. I think that we can pretty well guess that much under the current circumstances, but you'll probably get an official announcement in the next few days or a week about what exactly will happen. But I think just realistically speaking, the way the government has been going about things, face-to-face exams won't be happening pretty well for any university unless there's some absolute need, in some particular subjects. It might be professional accreditation, or you might need to do a lab experiment as part of your exam. But since we don't have to, we'll have some alternative, so don't worry about it. You'll be informed in the next few days. Okay, any questions? Sorry, 3:55. Any questions? Yes, no, indifferent? Okay, we've got a good turnout. I didn't actually see who was here today. Oh yeah, quite a few. I can see through that, I can manage who's here. Okay, if you don't have any questions, then go away and work on the prac sheet, and I'll see you on, when do we see each other again? Wednesday? No, Thursday, different class. Thursday, yeah. Okay, everybody happy? More or less? Oh,
I think one person's asking in the chat, yeah.
Sorry? Yeah, there is
one person's asking in the chat.
Assignment. Yeah. The assignment will go up. Sorry, the weekend was again one of those things where you ever have those weeks where you think I'm going to have an hour to sit down and do something, and nothing happens, or you don't.
Every week.
Sorry, all the time. Yeah, I mean, today I've just been meetings and classes since 9 o'clock, and I've still got another one just about to start, which is a lot of fun. Okay, just watch out for the assignment. It will appear, and I'll make it a short, sharp one for you, so don't worry about it too much. Okay, if everybody's happy, we'll end the meeting, and I'll see you on Thursday in a Zoom link. Yep. See you all later.
Thank you.
Yep.
Cheers.
Thank you.